closely at the exact angle of this aircraft's wing in a wind tunnel, engineers didn't choose this profile for aesthetic reasons. It is mathematically calculated to push drag to its absolute physical minimum while keeping the plane aloft. In circuit design, the goal shifts. Here, engineers must tune the resistance of a load to perfectly match a source, extracting the absolute maximum power possible without losing energy to heat. And in computer science, training a neural network means systematically adjusting millions of parameters to drive the model's error rate to the lowest possible valley. Across these disciplines, engineers do not design for arbitrary outputs. They design for the exact boundaries of physical and digital systems, the absolute maximums of efficiency or absolute minimums of error. Finding these exact limits relies on a unifying mathematical mechanism known as optimization. This split screen shows three curves: an aircraft's trajectory, a voltage wave, and a loss curve. Extreme values are found by tracking the rate of change to the exact point it stops changing. This location, where the derivative equals precisely 0, is the critical point. The zero derivative defines the optimal state for each of these systems, whether the underlying physics involves airflow, electron flow, or data processing. On a Cartesian grid, a tangent line rides along a continuous function, f of x, representing the instantaneous rate of change. Plotting this numerical slope on a synchronized graph below reveals our critical point, c, exactly where the tangent goes horizontal and the slope hits 0. But finding where the derivative equals 0 only tells us the system has momentarily stopped changing. It does not identify whether the system has hit a maximum peak or a minimum valley. To determine the nature of the extreme, we check the surrounding slopes. If the rate of change flips from positive to negative, we have a peak. If it flips from negative to positive, we have a valley. We bypass checking surrounding slopes using the second derivative test. Testing concavity directly at the critical point, a positive second derivative confirms a local minimum. Conversely, a concave down curve, yielding a negative second derivative, confirms a local maximum. Locating where the first derivative equals 0 and verifying the concavity with the second derivative provides a universal mathematical framework for locating the perfect state of any system. We can move this out of the abstract plane and apply it directly to the physical reality of aerospace design. For an unpowered glider, the primary engineering objective is maximizing the lift-to-drag ratio. The higher this ratio, the further the aircraft travels on a given loss of altitude. This diagram maps the glide ratio onto our calculus framework. Differentiating the function, accounting for parasitic and induced drag, and setting the derivative to 0 isolates the optimal lift coefficient, exactly the square root of parasitic drag divided by the induced drag factor. By simply setting a rate of change to 0, aerodynamicists derive the exact parameters required to keep an aircraft in the air with maximum efficiency. We see the exact same mathematical logic govern circuit design, specifically when solving the problem of delivering maximum power from a source to a load. Our circuit's source voltage, internal resistance, and variable load resistance trace a parabolic power curve. Setting the first derivative of power to 0 simplifies the complex fraction, proving the absolute peak occurs exactly where load resistance perfectly matches the internal source resistance. Analytical calculus proves that maximum power transfer is mathematically impossible unless the two resistances are identical. Some systems, however, are too multidimensional to solve for 0 analytically with algebra alone. In machine learning, training a neural network requires minimizing a complex cost function, like mean-squared error, across thousands or millions of parameters. On this 3D error surface, the gradient descent formula calculates the first derivative to navigate the steepest descent. Taking iterative mathematical jumps, the gradient approaches 0 and the steps shrink until the weights settle at the absolute bottom basin of minimum error. The famous gradient descent algorithm is just an automated, iterative search for the critical point where the rate of error change hits 0. We can bridge continuous analytical mathematics and discrete computational logic by automating this optimization process. We must script how large of a square to cut from a flat sheet's corners to fold a box with maximum volume. The flaps fold upward into a 3D container. Below, we map the volume objective function against the corner cut size. The script's first programmatic task is defining this continuous objective function mathematically, establishing volume purely as a function of that corner cut. The code calculates the first derivative, stopping exactly at the peak where the derivative hits 0. It runs the second derivative test, checking concavity to confirm a true maximum. Finally, it outputs the optimal corner size, and the box snaps to its maximum volume. Because this physical object exists on a closed interval, meaning you cannot cut less than 0 or more than the sheet itself, the script also verifies these physical boundaries against our critical point. This simple geometric code relies on the exact same logic used to map glider aerodynamics, balance circuit loads, and train multidimensional neural networks. Whether solving for circuit impedance or programming physical geometry, optimization translates physical limits into the universal language of derivatives.